And let's have a look at the exercise. So that is the design we made. We have a MEMS chip that is mounted onto a printed wiring board. The attachment is an adhesive, and we already computed the stress in the chip, and now we have only two more tasks to solve, and I think we can manage this today. And probably some of you have seen my last recording, which is on solder joint reliability. And so in that way, we are going to estimate the number of cycles to failure which this flip chip attachment can tolerate. And yeah, that's one of the questions. So so that is, with this design you must solve the following technical problems. Solder joint reliability of the controller, it must survive more than 1,500 cycles, and the cycling is between -25 and +135 degrees centigrade. There is one more question which we also have to address. That is, we have the information that the longest digital conductor line is 72 millimeter, and to that purpose we must calculate the time of flight of or the total running time of a digital signal, and we also must check whether it is necessary to apply the transmission line model. Okay. The second question is a minor one, but it can also give you 10 credits, and 10 credits can be of high value when we are going to evaluate which grade you will get for your exercise or for your exam then. Okay. What have we done? We have done the thermal management. Also, I said the complete assembly should be consistent. And for instance, in our thermal management, we had a path. So from the junction area, which is the source of heat, the heat will go through the solder material, then it will go to a printed wiring board, then it will go to an adhesive, it will go to copper. We again go to an adhesive, we go to the sink and to the air. And so for us it is important to know the CTE problem between the silicon, in that case of the flip chip, and the printed wiring board, and what the effect on the solder joint reliability is. Okay, we have already seen some information. For instance, we have said the thickness of the solder material is 0.2 millimeter in the thermal management. So of course we should be consistent with that information. Another thing which we already took here is, for instance, for the substrate, we took Young's modulus of 12 gigapascal. That will not be necessary in our exercise here, but for the substrate we selected a CTE of 14 times 10 to the power of -6 per Kelvin, and for the silicon 3 times 10 to the power of minus 6 per Kelvin. And now let us start. So we're dealing with solder joint reliability. And the main question is, why will a solder joint fail when it is cycled 1,500 times from minus 25 to 135 degree centigrade? So the delta T, here it is 160 Kelvin. And what happens in a solder joint, in a flip chip or in a BGA? And here we just make it simple. So when we heat it, what will happen? Of course, oh no, I made a small mistake. Maybe it's better to start with the substrate. And we have the chip on top. What is the relevant length? Of course, it's not the size of the chip, but it is more or less the clearing of the outermost balls here. And now what will happen when we have a temperature change? So in that case, it will go out a little here, but it will go out much more here. So that's the expansion. So let's say we regard only 1/2. And on the other hand, when we cool down, what will happen? Then something like this will happen, and in that way we get the thermal cycling, and in that way we will get shear load. It is important to make yourself to know how shear is defined. The shear is the delta L per side. The total delta L can be computed, so it's a delta L half divided by the height of that solder joint. In fact, in real BGA, the situation is a little different because we have more balls, and having more balls in the middle will be like a stress relief for the outermost chips. So what else is important. What is the delta L? Of course, it's thermal expansion, and that's the length difference between the substrate side and the silicon. And in that way, we can say the delta L is L0 times the delta alpha times the delta T. So the alpha silicon we already defined. The alpha for the printed wiring board we also defined. So here we said it's 3 times 10 to the power of minus 6 per Kelvin. And here it is 14 times 10 to the power of minus 6 per Kelvin. Okay. So that's a total delta L, and as it is a square device, so we must take the diagonal, and so we must multiply it with the square root of 2, and so the shear is L0 times delta alpha times delta T times square root of 2 divided by 2. Did I forget something? Yes, I forgot the age. We already defined age is 0.2 millimeter. What else do we need? We didn't define this L0 here, but it's a normal microcontroller, and in that way we are relatively free to define it. I think in the thermal we took something like 5 millimeter square, so not 5 square millimeter, but 5 millimeter square. So I would say if we define it that way, or if we say it's a little less, so 4.5 millimeter, that would be a reasonable value. So the shear strain is 4.5 divided by 2 times 11 times 10 to the power of minus 6 times, what was it, 160 times square root of 2 divided by 0.2. And now I just need a calculator, or does someone else already have it? 2.25, enter. Times 160, 1.41 times was that also your result? Can you speak louder, please?
Yes, this is my result.
Okay, so it is 2.8%. So normally in engineering we use for strain we use percentage, but here in the calculation we use absolute value. So in fact I must say it's a relatively high value we can see. Now we must look for the uniaxial strain. That's the shear strain divided by square root of 3 roughly. It's not very precise, but it's a good approximation here. So, and that is divided by, what is it, something like 1.6 or so, and that's no, 1.7 it is. So yeah, so I get here 0.16, so it's 1.6%. And now the question is, how often is that tolerated? And to that purpose, we must address the Coffin-Manson diagram. And that Coffin-Manson diagram says something when we plot here the log delta epsilon, and here we plot the log NF. It is such a linear behavior in that log-log plot, and the slope is given by some exponent. So typically the formula is NF is C1 times delta epsilon to the power of C2. And now in our lecture for our estimations, we can say C1 is roughly 2, and the delta epsilon, the C2 is roughly minus, let's say, 1.3. And now let's compute NF. Again, we and you also will need a calculator in the exam, of course. So and so I get some value like 214 as a NF when I put these data in here. Okay, so we didn't solve the problem. What can we do now? So we are quite far away. If you're only a little far away, of course, we can again play around with parameters. But because we have fixed most of the parameters already, we do not have too much of a choice. And therefore, we use a joker, and that joker is an underfiller. No. What's the effect of an underfiller? Yes, I would rather say it's more than a stress relief for the solder joints. So in fact, the result is that the strain differences on the solder joints are not so large. So take strain. Okay, and NF with underfiller is more than 10 times NF with no underfiller. So NF with underfiller is roughly 2140, and that is more than 1500, and so we can say solved. Okay, so in that way we can estimate what the solder joint reliability will be, but be warned, in real life it is not as simple. What I demonstrated here is just to show you what the problem is and what the physical and metallurgical origin of that problem is. Also, you got a first introduction into fatigue, and so from now on you know that a constant load is different from a variable load, especially if the variable load is cyclic and repeating all of the time for thousands or tens of thousands or even millions of times. At some time we will have cracks, the cracks will propagate, and the devices which were joined so neatly will fall apart. And in that way, at least we have a first glimpse how to analyze the problem. Now let's come to the last portion, which is the transmission line analysis. Yeah, please go ahead, but louder, please. No, in fact, it's not, because also when you make a sketch or something, you should clearly mark the middle of the solder joint, yes? Here. Because what is longer here, it has no effect on the fatigue, yes? So you take... Yeah? The L0 is the distance between the the balls along a length. But on the other hand, we also have balls. We have balls, of course, here, yeah, and the length in the diagonal is of course, because it's a square device, L0 times square root of 2. And I took for the length here, I said a little less than the size of the chip is, yeah. So maybe I also should mark here that is low T and the red it's glowing hot. So it's the hot side here. Did that answer your question? Okay, good. So, transmission line. So, imagine we have a conductor line, and now we are talking about digital signals. So that would be the conductor line, and here I'm only interested in the time of flight and not in the total traveling time of a signal, because that would have to be computed in a more complex way. So we only look at time of flight. So we have a signal. So let's say here we have the voltage or potential, and it comes along here and it travels along that conductor. And normally, what's the time of flight of such a signal? That's length divided by speed of the signal. So what's the speed of a signal? How fast is an electrical signal on a line? Yeah, divided by square root of epsilon r, which is permittivity. In fact, we must say the effective permittivity, because in some cases, we do not have a material on top of our conductor. But here, in most cases, we have some epoxy material, which is a solder resist. And in that way, probably our complete line is covered. Oh. So, what do we have to take here as a epsilon r? Give me just an estimate. For a polymer material. So let's make it simple. Here we take a 4, and here we take a 9. So there are variations, of course, but why did I select it? Because the square root of 4 is 2, and the square root of 9, it's 3. So it's easy to estimate. The speed is, so we have a polymer material, it's the speed of light. That's 300,000 kilometers. That means 3 times 10 to the power of 8 meters per second divided by 2. Printed wiring board is a polymer. So that's 1.5 times, I hate this, (10 to the power of 8 meter per second). So time of flight is What did we say? The longest line is 7.2 millimeter. Times 10 to the power of minus 3 meter divided by 1.5 times 10 to the power of 8 meter per second. So that is, so I need my calculator. Oh. It's something like 5 so that's 5 times 10 to the power of minus 11 seconds, and that is, what is it? 50 times 10 to the power of minus 12 seconds. So it is, what is it? 50 picoseconds. Was that correct? Just have a look at the so yes, 300,000 kilometers is 3 times 10 to the power of 5 kilometer per second. And so it's 3 times 10 to the power of 8 meter per second. Okay, should be correct. Maybe you can recheck it. In mind I had 500 picoseconds, but maybe you can have a look. Okay, that was the easy part. Now the next part is, do we need transmission line model? The transmission line model must be used when the leading edge of a signal when the conductor line is larger than the L edge divided by 2, then yes, we need transmission line. So what is L? L is 72 millimeter. And what is the length of the leading edge? That is the time of the edge and time and length of the edge are connected via the speed of the signal. Yeah? So the length of the edge is the time of the edge times the speed. But what is the time of the edge? Here we use a rule of thumb which says time of edge is roughly 0.07 divided by the frequency of the clock. And now we make an assumption, what's the frequency of a clock of a microcontroller as a flip chip? Yeah, we can. Yeah. Here it is given. Yeah, sometimes I don't give the information. So it's 1.5 gigahertz. So T clock is the inverse. So it's 67 times, no, it's 6.7 times 10 to the power of minus 10 seconds. So it's 670 times 10 to the power of minus 12 seconds. That's the T clock. And of that we take 7%, 0.07. So TH is 4.7 times 10 to the power of minus 11 seconds. And that has to be multiplied with 1.5 to the power of 8, so LH. And so my result here is 7 times 10 to the power of minus 3 meter. And LH half is 3.5 millimeter. Yeah. So L is larger than LH half, and in that way, and that's something I want to see in the exam, that you say yes or no. Yes, we need TLM, so that is a transmission line model. And with that statement, we are finished with the exercise. So I have tried to show you what I would expect in the exam, how you solve this. In the exam, you will have 2.5 hours, In fact, typically if you prepare yourself well and perform some exercises for yourself or in a team, then you will be prepared well. And also what is necessary, that you generally have a reasonable understanding of assembly and packaging and of materials, processes and design, and in that way, so I think most are quite successful. So the average grade is typically like 2.1 or so over the last years. So I think it's solvable, and I wish you good luck. Do you have more questions here? Yeah, go ahead. No, that wasn't specified. So I would say it is not necessary. You just take it. Let's say the assumption the conductor is embedded in that polymer. Yeah, you could also say, okay, what's the situation if a conductor line is on top? You could say part of the electrical field is in the air. Air has one, so here you would have a not so strong effect. But for a conductor line in a multi-layer, which you always have, you typically have at least 4 layers in a printed wiring board. Here you can also always say it is completely embedded. Yeah. So if in anything where you are going to have to make an assumption, yes, if you are not quite sure if that is correct, then you just write down 2 words or so. Why? Yes. So if you are not sure, shall I take 4? Maybe you just write because embedded in printed wiring board or embedded in PCB, then you just write 2 words. That doesn't cost you time, but it's always an explanation for me that you have thought about it. Yeah. No, you will have no lecture notes, nothing. You have a calculator, a ruler, and also what you are not allowed, under no circumstances, you use red pencil or red pen, because that is my privilege to, when I correct. So it would mix up things in that way. Yes, I would expect that you keep in mind some of the properties. Maybe you also will see at the end of the lecture notes there is a table where some values are there. You can use also. You got some data which I used here. So I'm not so keen of giving such data too precisely, yes, because in most cases you get the material from a different manufacturer. It's quite different CTE, different Young's modulus, and so on. And so it always should be in a reasonable range. Yeah, that's important for me. I would say more precise than just the order of magnitude, but so I have some the feeling that you know, what is typical property of a material. You have more questions? If not now, you can anytime you can send me an email. Another point is, as I said, it is very desirable that you form a learning group of 2 or 3 persons, and I think there are more exercises you find at the Fachschaft and more previous exams, and there you can take the examples of such design projects. Also, there are more in the lecture notes, and you try to solve these in a group. That's always better, because sometimes one thinks, oh, I could omit this, or that's not so important, and some other person says, no, I think it's really important, and so just to have a cross control, it is very advisable that you do such exercises and go through these. And so maybe a week before the exam, we can have a meeting. Of course, it will be, again, an electronic meeting like this exercise. And when you send me questions before that meeting, I can prepare myself, and then I will go through all of your questions, and so that will be some kind of counseling lesson. And after that counseling, you can still have a week or so to maybe to modify your preparation. That's my idea, and so that's the way I did it in the last years. But one thing is important, I will do this counseling only on request. So if nobody requires it, I will not do it, yeah? It's up to you. Yeah, louder, please. Yes, better. My idea is, yes, and we have quite a number of textbooks in the library. It's only individual ones, you cannot borrow them, but but there is so much, let's say, wide information. I think I tried to put the most important things on assembly and packaging into that lecture and in my lecture notes. So normally professor should recommend some textbook, but in that case I don't know anyone which could prepare you in a similar way. My idea is more, you try to go through the exercises, and if you have some questions, yeah, look, for instance, just in Google, or better in Wikipedia. Yes, there is, for individual processes like wire bonding or sintering and so on, you find more detailed information. Yes, and so I would say try to prepare yourself to the exam, because you more or less know what you have to expect. Prepare yourself for this. When you prepare yourself thoroughly, you will also have a good understanding of assembly and packaging. And if you have specific questions, either address me or look it up. Yes. I would say you can try for a textbook, but I would not say it would waste your time, but maybe a textbook is better in a situation when you go deeper in the topic. For instance, we have the lecture Advanced Assembly and Packaging, and if you have more questions there, then there are more specific textbooks, for instance, on sensors packaging, or on power electronics packaging, or on printed wiring board, surface mount technology. But I think, if you are interested to proceed your career with assembly and packaging, then I would say, then I advise strongly you look up textbooks. Okay? Then, okay. Then see you in a few weeks. And I will upload the latest version of the exercises. And so if you have questions, email it to me. Good luck. Goodbye.